So for number 43, we want to find out if this sequence over here, if it converges. And so a sequence an converges if an tends to a specific limit as n approaches infinity. So what we're going to do here is we're going to take this limit, so the limit as n approaches infinity of cosine squared of n divided by 2 to the power of n, and see if we get a limit. And now this is actually two functions multiplied, right? This is 1 over 2 to the n, cosine squared of n. And the reason that I'm separating is so that we can talk about them in parts. So the limit as n approaches infinity of 1 over 2 to the power of n, this is pretty easy. This is just 1 over 2 to the power of infinity is equal to 1 over infinity. That is going to give us 0, right? But what about the limit as n approaches infinity of cosine squared of n? Now cosine does not converge because cosine just goes, it takes all the values between 1 and -1. So it just goes 1, -1 like this forever and ever, right? So it never converges. Cosine squared, it also does not converge. The only difference is that instead of going from -1 to +1, it goes just from 0 to 1, right? Because it can't have negative numbers. But it still does not converge. So this limit does not exist. So how can we find a limit if this limit over here does not exist? Well, we're going to have to be a little bit clever and use the squeeze or the sandwich theorem. And these basically say, and I'm going to show them using functions, but it's also perfectly valid for sequences. So it says, hey, if we have, I'm going to call this point here A, and this point over here L, right? And I'm going to say, if I have a function, I'm going to call this f of x. And we can see here that the limit as f of x approaches a, it's just L. And then I have this other function that is less than f of x, right? And also has a limit at L. I'm going to say that this is g of x. And then say that there exists another function that is less than f of x and bigger than g of x. So it exists maybe here in the middle, and this is h of x. And we can see here that if h of x is less than the blue one and greater than the yellow one, and if the lower and the upper function, they meet at this point here at a and L, then it means that also the limit of h of x as x approaches a, it must also be equal to L, right? So this basically says, hey, if a function is kind of sandwiched between two other functions, and the two outer functions, they have a limit as x approaches a specific value, then it will also be the limit of the middle one. And so we're going to use the same principle here, and we're going to say, okay, cosine squared of n over 2 to the power of n, this is definitely less than or equal to 1 over 2 to the power of n, because 1 is the biggest value that cosine squared can take. It can't take anything bigger than that. So we're going to say that this is greater than or less, this is 1 over 2n is greater than or equal to cosine squared of n. And we can say that this is definitely greater than or equal to 0 because cosine squared n can't be negative. So it can at most be 0. And so we have shown that cosine squared is the middle function, where the upper function, this would be 1 over 2n, or the upper sequence, and this would be 0, and then this would be cosine squared n over 2n in our analogy, right? And we have shown that it meets this criteria, and now we're going to take the limit as n approaches infinity of 1 over 2n, and the limit as n approaches infinity of 0. And this limit here is 1 divided by 2 to the power of n, that is 2 to the power of infinity. So 1 divided by infinity, that's just going to be 0. And the limit as n approaches infinity of 0, well, that's just equal to 0. And we've shown that, hey, these limits are 0. Therefore, the limit as n approaches infinity of cosine squared of n divided by 2 to the power of n is equal to 0. We've shown that through this squeeze theorem. So once we've shown this, we can now say thus so we can say, not thus actually, an approaches 0 as n approaches infinity, so an converges. So we've shown that an converges because of the squeeze theorem.